towards it without having to like solder or anything.
All right, so we can begin whenever you're ready, Jonathan. Thanks for joining us, Jonathan, and I'll let you get started.
Yep. Let me see if I can do the screen share.
And I'll leave us unmuted for now. If that becomes a problem, just let me know and we can turn on mute, but it makes it easy for anyone that has questions that just start talking.
Okay, is the screen sharing working?
Looks great. Yeah.
Cool.
Yep. Everyone else?
Okay. And okay, so we're ready to get started.
Yeah.
Okay, perfect. All right, so well, hi everyone. I'm Jonathan. I work on the Perl 6 and various bits of machinery beneath it. I originally created the MoreVM virtual machine and worked quite a lot on the Recruiter Perl 6 compiler. My role in Perl 6 design actually came fairly late. I was definitely on the implementation side for a long time, and then somebody needed to care about the Perl 6 concurrency, and that eventually fell to me. I was doing that kind of stuff and teaching about concurrency in other languages as part of my work at Edgement, which is where I'm working. And so it was kind of a natural thing to end up working on. So what I want to do today is to talk quickly through a bunch of Perl 6's concurrency primitives. I then want to talk about how we take them and put them together. It's not very difficult to have a single concurrent operation going on. After all, that basically devolves to synchronous and non-concurrent programming. What gets fun is when we have multiple of them and we need to deal with different things happening at the same time, and bits of sequencing, bits of dependencies, and so forth. So we'll take a look at how we might compose different concurrent workers of various kinds. And then we'll take a look at some practical examples, and hopefully they'll have some relation to the sorts of things you work with. They're based loosely around the idea I was given of what sorts of problems you work on. So digging straight into the primitives. I find it quite helpful to, when I look at the language and see what sorts of concurrency features it has, to try and fill out a table like this. So this table is just really saying, how do we represent one value or a sequence of values, both in the synchronous world and the asynchronous world? And by the synchronous world, I mean where we either just ask for the value and we wait for it to become available, or with a sequence of values, we're just saying, give me the next one, give me the next one. Whereas with asynchronous, we're setting an operation off, and it might produce one value sometime in the future, or might fail to do so. Or with a sequence of values, it'll produce maybe many values in the future. And we want to react to them, but we don't want to sit around waiting for them because there might be lots of different things that are going to produce those values. So starting out in the top left, one value synchronous, well, that's dead easy. That's just the value itself. So values in Perl 6 know what they are. So if I just say .what on here, we see 42 is an int, pshibye is a string, and there we have a shopping list instance, and it knows what type of object it is. So, okay, nothing challenging there. So sequences of values. A sequence of values is represented in Perl 6 by what we call...
You gotta go back and explain what that second one was, though. That looked pretty cool.
This looked pretty cool.
What's that second word? I know what 42 is, but what?
Oh, pshibye. That's the Czech word for story.
Oh, okay, great.
It's just a random Czech word they picked because it had loads of diacritics.
Gotcha. Yeah, that's cool. Thanks.
Yep. Okay. So okay, back to this. How do we represent a sequence of values synchronously? Okay. Well, how do we pronounce this type name? Is it sec or seek? I don't know. I've been saying sec for ages, and then I keep meeting people who call it seek because, you know, sequence. So call it whatever you like. But the idea of this is it's something that can produce values on demand. So this is a bit different from saying that we have an array or a list, which is something that stores values. A sequence is something that knows how to produce the values, but it won't do anything until you actually make it do so. And that means that it is a good way of dealing with laziness. That is where we just get values on demand and only get as many as we need, but also infinite things. So where we have a sequence of indeterminate length. And of course, if we try and ask for all of it, we're in trouble. But normally we don't care to do that. The other really important thing about this is it doesn't remember the values. And if we just look at one place that this shows up in Perl 6, doing a bit of basic I/O, so we just open a file there. A lot of the output I'll show you, by the way, is taken from sessions in the Perl 6 read eval print loop, and then I've just tidied them up just a little as well. But there we have a file handle. It's open. And then I say, give me the lines. What have I got? Well, that's a sequence. And at this point, I haven't actually read any lines from the file. But if I say, well, get the two things at the head of this sequence, and then just give me a representation of what they are, well, what I get is a sequence that has two things in it. And the .perl there actually forces it to tell me what's in there. And it's only at that point where I call .perl on this that it finally goes to the file and says, well, actually, I really need to read something. And it does that. So if I do it again, you'll see it's actually stateful in that sense. It's a new sequence object, but it's got the underlying file. And then at the end there, we'll just do a grep for everything that's in that file that contains Perl, and map that out into the number of characters per line, which is basically useless. But it also shows you that we can at this point grab all of the stuff, see all of the lengths, and then we're at the end of the file there. And one of the nice things to note about that is that with things like grep and map in Perl 6, they also work lazily. They don't actually do any work. The only thing that's made this do work is that the read eval print loop here wants to actually print out a list of results for me. Okay, so that is basic sequence stuff. And how is it synchronous? Well, it's synchronous because when I ask it to give a line for me to grep, or for map to map, it's only then that it will go and do the I/O. And if that takes time to go down to disk, of course, a lot of the reads will come straight out of an in-memory buffer, so it's cheap, but occasionally we'll have to go to disk, and that will take a bit of time. So we pay the cost of that work at the point that we demand it. Okay, everyone happy so far with this?
Yeah.
Okay. Yep. Okay. Now, it turns out that sequences actually provide a concurrency mechanism. And this is not an overly typical thing to do for something with side effects, but I'll show you just to give you an idea of what is going on here. So gather and take are a construct for producing a sequence. And the code in gather will just run at the point that we ask for a value, and it will run until a take happens, and then it will just be suspended at that point. And it won't run again until we ask for another value. So if we are making a little bit of a guessing game, and this is one of the first programs I ever wrote when I was a little kid, not with gather and take, I should say. But here we just have a sub-guesses. We take the name of the player, and then we immediately return a sequence, and we don't enter into this loop yet at all. We just return a sequence, and when it asks for a value, we'll end up in this loop. And we're going to have two players in this game. So a sequence actually is an iterable thing, and we could grab the iterator from those. And you don't normally, for most things, have to work in terms of the raw iterator API, but we want a bit of control here over exactly when things are evaluated, just to make clear what's going on. So here I just sit in a loop, and I do pull one, and then I take that value. So how is this used? And we'll come back to this code in just a moment. Well, here is the game. So we just pick a number out of the range between 1 and 100. In another little bit of laziness in Perl 6, 1.100 does not actually make a list. It's a range object. And we can just very quickly pick a number out of there without actually iterating it all. So this is kind of nice. So we have a number, and then we just do a for loop here, and we say we want to alternate between the guesses of player A and the guesses of player B. And then we just do a bit of a when construct in there. So when the number is what we expected, they win. When it's too low or when it's too high, then we say so. And what happens when this code is executed? Well, when we hit the alternate line, that makes the sequence objects. And then when we enter the loop, we need a value. We need a value to invoke this loop body with. That becomes $_, which is what the when is working against. So here we say, okay, finally we'll have to actually enter this loop on the gather. So we enter the loop and we hit pull one. And the pull one forces us to enter the loop in here. And we do the prompt. We ask for a guess from player A. And we take that value. And at that point, this is suspended, alternate is suspended, okay? And we end up back here in the loop body. And if they don't guess right, then we need to have another guess. And you'll see this code is resumed. And then we do a pull one here, okay? And this time we're in the version of this that was for player B. So it keeps the state there. It's just lexical scoping going on. And now we take a guess for them. And so we go on and around this loop. So this is essentially a cooperative concurrency control mechanism. It is a way of being able to have bits of work running and then suspending them and letting the thing that wants the result of that do its bit of work. This is quietly useful. In fact, often so quietly that people don't even realize there's concurrency going on there. But the thing to take away about this is that we have with gather take and the for loop essentially a way of composing these different concurrent workers. And just hold that thought a little bit, because we'll come back and see exactly how you do very similar things with asynchronous values. Okay, so that's our table so far. So we've filled out, okay, the synchronous row, and now the asynchronous row. This is a little bit more interesting to dig into. So a single asynchronous value in Perl 6 that is represented by a promise, and we call it a promise because it is the promise of a result or a value in the future. So I can just make a new promise object by saying promise.new. If I ask for its status is planned. We plan to keep or break this promise at some point in the future. And then we can keep the promise, in this case with the value 42. We, at that point, can ask for its status, and its status is kept. And then the result is 42. So that's a promise. Now, of course, the reason promises get interesting is because the thing that keeps it or breaks it is often quite some distance away from where it is used. Now, when I try to do a computation synchronously, and that computation produces a value, it's possible it will fail. And if it fails, we get an exception. Well, when we do an asynchronous computation, of course, it can fail too. And how do we get the exception? Well, a promise can also be broken. So if I just break this promise with an error here, I've just been lazy and thrown a string in there rather than some typed exception, then the status will show up as broken. And if I ask for the result, the exception will be rethrown. And this is fairly significant because what's happening here is the exception is being transported to the place where the result is consumed. But along the way, to help with debugging, and it was a one-liner, so it wasn't so fun. But you can see here, it tells me where I tried to get the result, but it also told me the original place where the exception was thrown as well. And it will actually, if you have a chain of different places you were waiting, it will tell you the whole chain of places where you were trying to get the result and then you failed. And that's very helpful when you have a sequence of different asynchronous operations that depend on each other and you want to see where things broke. Okay, so that's promises on their own. Let's just see a small example or two of how they're used more realistically. So normally a promise is kept or broken by an operation that's running concurrently. It could be some code that's running on a thread somewhere. It could be some asynchronous bit of input or output. So let's do a computation first. So here, I just needed something that was expensive and took time. So I could actually type p.status quickly enough to see plans. So what I've done here is I've got the start keyword. And start means run the statement or the block of code after me on a thread in the thread pool. So it doesn't start a new thread necessarily. It just schedules it onto a pool of them. And give me back a promise. And this promise will either be kept when the computation completes, and it'll be kept with the result of that computation, or it will be broken if the computation throws an exception. What am I computing here? That 3 dots is called the sequence operation. And on the left side of it, you see I have a list of 3 things. It's the integers 1 and 1 again. And then this star plus star is actually a closure that means take an argument and then take another argument and add them together. So it's whatever plus whatever. And in the context of a sequence, that means add up the last 2 things. And that means this is actually the Fibonacci numbers. So it's 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so forth, all the way up to infinity. And we just compute the 100,000th one of those. And if I do this and I quickly enough type p.status, it says, OK, this is still planned because we haven't completed the work yet. And then later on, it says, OK, it's kept. And then I can ask how many characters is the 100,000th Fibonacci number. And it turns out that it's more than 20,000 characters, which is why I just printed out the number of characters rather than the string there. It wouldn't really fit. Okay, so one thing to realize about this is a promise is something that start produces, but start is not the only way to get a promise. Okay, so another way is some kind of asynchronous input and output. So we have a process async class built into Perl 6. This is just a way of running a process asynchronously. And here I'm just running the shell and sleep 4. And that gives me back a proc object. It isn't started yet because we might want to do some other bits of setup and configuration. Here I don't want to. I'll just say start the process. And that gives me back a promise that will be kept when the process exits. So if I quickly type exit status, it will still be planned because we haven't finished that process yet. It is still running. And then afterwards, it'll be eventually kept. And the result is an object from which I can get the process exit code. So that's a couple of examples of promises. And promises are your way of conveying a single result, a single value, or potentially the passage of a single amount of time. We'll see an example of that in a bit. Okay, everything good with promise so far? Okay. Yep, good. So finally, we have this this other slot in our table here for an asynchronous sequence of values. That's called a supply. And supply has a lot in common with sequence. It's kind of almost a mirror image. If you know anything about category theory, actually it's the dual of a sequence. Now, the interesting thing about a supply is that it looks at first glance a lot like a sequence. You can map, you can grep the values, but unlike with a sequence, where if I want a value, I pull it. And if there's a chain of map and grep, we go to the map and say, give me the value. And the map goes to the grep and it says, give me the value. And grep goes to wherever the data is coming from. And we block all the way. With a supply, instead, the values originate at the top of the chain. Maybe they arrive from a message queue or from a timer being fired or over the network. And instead, they are then pushed. So the value is pushed into the grep, and if it survives, it's pushed into the map, and the result of the map is pushed out of there to whatever cares about it. So this whole chain of operations react, and that's why we call it reactive programming. So one simple thing you can do with this is a kind of publish subscribe. So I'll make a supplier, and a supplier is basically a mechanism we can use to publish out values to a supply. And I can just ask that to give me the supply. So the supply is the thing that you subscribe to, if you like. So what I've done here is I've said supply.tap. So I want to tap this supply. And I'll just pass a closure in there that says got $_, and that will run whenever a value is pushed through this sequence. So if I just say source.emit, and I emit the value, then that supply will be tapped. Sorry, that supply that we tapped earlier will have the closure that we tapped it with run. So it'll just say, oh, I got chili. And there's no concurrency or no threading introduced by this. A supply is actually a mechanism of controlling concurrency more than introducing it. So if I take again this supply, I can this time tap it, but first I'll do a map, and I'll just map it to uppercase. So that star that you see is it's the same mechanism we saw with star plus star earlier. It's just making a function that we're passing to map, and when it's called, it will call uppercase on whatever we give it. And then we tap it and we say, oh wow, whatever it is. And this time, if I do the emit, it goes to both of them. Okay, and again, it's a synchronous thing. It goes to one and it goes to the other. So here it's the sender that essentially pays for these. And that becomes quite important for later on when we talk about back pressure. So when I took this the supply and tapped it at the start, you'll see I stored something into the variable t1 there, and that is a tap object. So when we are doing an iteration, we might lose interest. We might say, okay, I've done enough times through this loop. I'll do last. I've seen what I wanted to see. And at that point, we let go of the sequence we're iterating over. That whole chain then becomes available to be garbage collected. But when we have some kind of asynchronous operation, particularly things like timers or network handles, it's not until we say that we've lost interest that we will be able to free up the resources. So management of these things that come back from tap is actually really important. So here, I'll just close the tap on T1. And what you'll see is if I just emit noodles now, only that second thing will get its callback. So this is what we call a live supply. That is, we are essentially at the point we tap the supply, there's a live sequence of values. We don't see anything from the past. We just see what's there now. And when we unsubscribe, then we lose interest, and that's the end of it. But the original source of values is still there. and we can tap into it again in the future. Other supplies are on demand. And the analogy with say, television, watching it live, or say Netflix, like a movie on demand, is very deliberate. That's exactly what we were thinking of when we gave it these names. And an on-demand supply is something that starts producing values when you tap it. And these show up in various places. So here, if I make an interval supply and I tap it, it's only when I tap that supply that it sets up a timer that fires every half second. Now, when I have an interval, what it actually does is schedule a timer to fire on the thread pool every, in this case, 0.5 seconds. And that means that if I sleep, then that is just going to fire in the background until I close the tap, and then it'll stop firing. And you can see that we have an event there roughly every 0.5 seconds. Another place that these come from is also the proc async again. So an asynchronous process will produce output, then we might want to collect it. So if we want to collect it, we can ask for the standard out or the standard error, and those are a supply. And the supply will just emit the data that comes out of the process. And this is pretty nice, because if you have both standard out and standard error that you're reading from, if you try and do this in a synchronous way, you kind of have to read from the two of them, or try to figure out which one to read from when, and if you get it wrong, it can deadlock because of buffers getting filled and so on. That whole set of problems doesn't really exist when we start doing it asynchronously. So what I've done here is I've just said, okay, I want to collect the output from standard out. Just concatenate it onto collected there, and then we'll start the process. We'll get the result. Asking for the result will block in this case, and then we eventually will have the exit code of 0, and then I can just print out collected, and I got the output there from PS. So lots of things are exposed as promises and as supplies. They are a standard way in the Perl 6 core library of dealing with either a single asynchronous thing or asynchronous things that produce 0 or more values over a time period. Okay, so we now have filled out our table, and that's our primitives. Okay, any questions before I go and start building up on top of these? Okay, I don't hear any. So
nope, nothing here.
Nothing here. Okay. So let's look at composing asynchronous operations. What happens when we have multiple of them going on? So what we really need here is ways that we can take one or more asynchronous operations, put them together, get correct propagation of errors, have them deal with, say, data safely if there's multiple threads involved, and that will, particularly with supplies, get that resource management correct, so we don't end up with resource leaks and things, which is a fairly common problem if you start doing event-driven styles of programming. So await is the first mechanism that I want to point out. And await here is a mechanism of saying I want to wait for an operation that's running asynchronously to complete. And in a way, this is a little bit like calling .result, except that it unpacks the value for you. It also turns out that you can await a supply, and that just means you want to wait for the final value that it produces. So this is just a rewrite of the example from earlier. We just await the promise that we started, and we get the result. And again, if there's an exception, await will rethrow it. Now, await is something that has been in Perl 6 since the Christmas release. Its semantics in Perl 6 Christmas are that it blocks the thread that's running until the result is available. Now, this was a thing we did to basically is what we had time to do. What we're working on in the upcoming Perl 6.d version of the language is that an await performed on a thread in the thread pool will actually just suspend the execution of that and give that thread back to the pool. And then when the result is available, we'll just continue running where we left off. And this will mean that whereas today, if you do 100 awaits, you're going to be in trouble and exhaust the thread pool. In the future, you'll actually be able to have, say, 1,000 or 10,000 outstanding await statements without causing any kinds of trouble. So let's just take a look at how we might use await in a slightly more interesting way. So here I am reading some JSON in from 2 different files. I want to pass it. So it might occur to me that I can read those and pass the JSON on 2 concurrent threads, maybe just to get me a little bit faster startup of the application or something. So if I say start passing foo JSON, start passing bar.json, I get back 2 promises. And with await, I can actually give it a list of things. And if I give it the list of different things to await, it will await the 2 of them, and it will return me a list of the unpacked values. And this is fairly convenient because it means that I can just do the list assignment on the left there, and then I have the 2 results. And I don't actually need the temporary variables there. I could just have said await start from JSON, whatever. I'd either have needed parentheses or to put the curly braces on the start form there to get it to pass right. So another way that you can deal with promises is by using anyof and allof. And these are used for sequencing. So these are not about when you're interested in checking if a promise succeeded or failed or getting the result. These 2 will never actually throw an exception, even if one of the promises you're checking did. But instead, they're just ways of talking about saying, well, I want to wait here or await any of these promises being done or all of them being done. Anyof is extremely useful for doing timeout style things. So this promise.in method that you see on the 3rd line there is a way of getting a promise that will be kept after 5 seconds. So this one can only ever be kept, but it's a way of dealing with time. So if I say await promise anyof, and then I take the exited promise that I got back from starting the process, and I wait any of that or 5 seconds to have elapsed, well, whichever one comes first, we'll get back the execution from await. Okay, and then we'll continue, and we can say, well, did it actually exit or not? And if you just take a promise and test it as a Boolean, what it will do is it will give you true if the promise was kept or broken, that is, reached a conclusion, or false if it's still in planned status. So it's a neat way of testing, did we get to some kind of conclusion yet? And we don't care at this point if it was successful or not. All we want to do is just kill the process off if it ran for too long. So that's some of the ways we can combine promises. Now, supplies turn out to be a good bit more challenging. And the reason is that we have these streams of values that are arriving, and they may arrive on different threads. They may arrive, therefore, concurrently. We also need to try and keep track of when we have finished dealing with all of the data. And we need to also maybe try to unsubscribe and clean up resources as well. So let's just take a look at trying to get these things right by hand, and then looking at the construct Perl 6 provides to do this well. So I'm just going to have an imagined little system here where I have trains. They can get delayed. Whenever we get a delay, we have a stream of events for each train, and it just sends out there the train code and the number of minutes that it's delayed by. And we have an application. The application connects over a WebSocket, so it can receive notifications and be told whenever there is a delay. So what we want to do is send to the application a list of train codes, from the application, a list of train codes that the user wants to be notified about. Maybe they bought tickets and they want to see, okay, is my train going to be late today? Will I make my connection and so forth? And then we want to batch up the delay information that arrives within 15 seconds. So we only send something once per 15 seconds to the user if there's anything to send. So whenever we get, say, a WebSocket connection in, we will call this user notifications subroutine. We'll pass in the relevant train codes, and this is going to return a supply. And we'll just make ourselves a new supplier that we can use to emit the results, and we'll return it. Well, not it, but the supply from it. And that can be tapped by whatever called it, and the results serialized and sent out over the WebSocket. So here we will just subscribe to the delays for each train. So we have a subroutine delay 4, and we pass in the code of the train, and we get a supply back, and we tap it, and then our callback will be called every time that there is some kind of delay notified on that train. And then we'll just make an array. We will do a little trick here with Perl 6 signatures. So if you take an object and it's got a bunch of properties, if I just go back a bit, you'll see that this has a train code and a minutes delayed. What you can do with an object is you can say, I want to pretend that this object is an argument list of positional and name parameters. And an object by default will just be a set of named parameters. And then you can just unpack it using a signature. And what I'm doing here is I'm just pulling the minutes delayed field out of that object. And then I'm saying, and I don't care about the other fields. That %% there means just put them into an anonymous hash, but it doesn't even bother doing it. It's just a way of saying I don't care that there are other fields in this object. And then we'll just push onto this latest array a message saying whatever the code is, that there's a delay, and it's delayed by a certain number of minutes. So now we need to send them, and we'll just do it in a fairly simple way. We'll just say every 15 seconds, I want this piece of code to run. And when it runs, we see, do we have any notifications? If yes, emit them. Just join them up with new lines and send them out there. And otherwise, we want to just clear. Well, sorry. After that, sorry, we want to clear that array so we don't send the same thing multiple times. So, that sort of looks kind of easy, right? I mean, to say it's dealing with asynchronous notifications coming in and time and so on, it's not crazily much work. The answer, of course, is not so fast. This code has some problems. It leaks resources, and it has data races. And if anything should go wrong somewhere, it doesn't actually convey the errors. They'll just kind of disappear somewhere into the ether, or they'll be thrown on some thread pool thread, and we'll just get an exception that maybe brings the program down. So where are the leaks? The leaks are here. So this is a WebSocket. At some point, the user will have taken their train, they'll be bored now, or they'll just not be looking at their phone. We'll have closed the WebSocket, but unfortunately, that supply of 15-second intervals will just keep going. And we won't be emitting the data to anywhere, but we'll still be getting it. The same with the one above there where we had delays for some code of train. Again, maybe that'll be coming from a message queue, and we'll have kept a subscription going from that. So how do we deal with this? Well, what we could do is we could make an array of taps. We could push onto that array each tap that we have whenever we tap something. And then at the end, we'll just say, oh, and whenever this supply gets closed, we should close all of the things that we tapped. This is a tolerable solution, I guess. It essentially works. It does have a problem as a general purpose solution, which is that there's various bits of code you can write where at some point the sequence that you have tapped gets to an end. So the things that you can have with a sequence are it can emit a value, it can have an exception, which we call quit, or it can be done. And if you have something which just taps over time, lots and lots of sequences that get done, you would just build up a huge list of taps that actually aren't particularly useful anymore. So this is not a general purpose solution to this problem, but it solves it for this particular case. But we still have a problem because I mentioned that this interval will run off in the thread pool, and we don't really know about this delays for subroutine. Will the delays all be pushed out on a single thread, or are there maybe multiple threads that get stuff from event queues and distribute them, and we might end up with multi-threaded code here. And in Perl 6, you cannot reliably push onto an array from multiple threads. An array is not a thread-safe data structure. And even if it was, if you look at the code that we have down below, we test if it's empty, and then we join it, but we might miss things being in there. But worse than that is that we join the things, and then after we've done the join, something else gets pushed in there, but then we clear it and we've lost a notification. So this is pretty horrible. And how do we deal with it? Well, we could go and stick a lock in there, and that works. It does the job. But by this point, we could be pretty disappointed because we have all of this boilerplate. It's pretty tricky to get right. We're liable to forget to get it right. And we really just want to write the interesting business logic. So that is why in Perl 6 we have supply and whenever. And a supply
Real
block.
quick, can you go over how does the lock work real quick? I'm not familiar with it.
Oh, how does the lock work? Okay. The lock, actually locks are pretty normal things in Perl 6 in that they have a lock and an unlock. And so when I do the lock operation, the lock will be acquired. If something else is holding it, I will be blocked. And then when I do an unlock, then I let it go, and anyone else who wants the lock can get it. Now, there's a horrible thing that you can get wrong with this, which is that if you acquire the lock and then you run some code and the code throws an exception, you have to make very sure that you release the lock. Otherwise, you don't, and then nothing else can ever get it again, and your program deadlocks. So in Perl 6, we also on log just provide this protect method. And if you pass protect a closure, it'll acquire the lock. Once it has done it, it will run the closure. It will then unlock it, and it will make absolutely sure that even if your code throws an exception or does some control flow that unwinds the stack over where the lock was acquired, it will always be unlocked. So it's just a method there to try and prevent you from having a problem.
Yeah, that's pretty handy. Cool, thanks.
Yeah, some languages do it with special syntax. In Perl 6, this is already pretty compact, for one. And for two, locks are kind of a last resort. They're a bit of a low-level thing, and there's nicer ways. Okay. So supply and whenever. The supply block is something that evaluates to a supply. So basically, it's the supply version of gather, if you think. And then whenever is a little bit like doing a for loop inside of a gather, if you want to loop over something inside of there, except it's asynchronous. We'll see in a moment. And then we have something called emit, which is like take to spit out a value. And the really important thing that supply and whenever does for us is automatic management of taps and automatic concurrency control. So let's rewrite our thing from before. So here we just say supply. You could say return supply if you wanted. And inside of here, we'll do a lot like what we did before, but instead of saying .tap and writing the closure, we'll just say whenever. And you'll notice the syntax of whenever looks a lot like a for loop. And actually, it really is a loop construct. You could even do last to say that you've lost interest in this particular source of data, and next to say I don't care about this particular piece of it as well. So here we just replace our .tap calls with whenever, but whenever automatically tracks the taps and closes them for us. So that gets rid of all of that boilerplate. And then we'll just stick our code in there again. I just did a slightly different way of getting the minutes delayed there, just interpolating that closure in the code, and that's it. Okay, it is completely safe. Oh, the other thing is we didn't have to make the supplier ourselves. We just say emit, okay, and that's all we have to do. So you might say, where is the concurrency control? And the concurrency control is done by a set of rules that the supply and whenever constructs enforce between themselves. So only one thread is allowed to be inside of the code of a supply block at a time. And that means the most obvious one is that no two whenever blocks can be running at the same time. They'll just be queued up and have to wait. But also, no whenever block can start until the supply block setup work is already done. So between these two, you get some pretty good guarantees. Now, one thing that is worth pointing out is the supply block, each time you tap it, essentially is instantiating this environment inside of it. So the concurrency control is per tap. And that means you really, really want to have your state that you're protecting inside of that supply block. If you know what actors are, by the way, and if you don't worry about this. If you know what actors are, you can think of a supply block being a little bit like one of those. It's not quite that, but it's very similar. Each time you tap, it makes an instance. The state is lexicals instead of attributes, but it enforces the one message processed at a time. Okay, so that takes us through supplies, and I want to finish it with practical examples. Any questions before I dig into a few final examples? Okay. So first of all, let's just look at a retry mechanism. So there's various ways to build these. The sequence operator that I showed you earlier is actually a pretty cute way to specify backoff strategy. I'll come to that soon. But I want to show you just a few ways of building some kind of retry mechanism. Now, first of all, let's try and build one that takes a synchronous operation or an operation that doesn't return some kind of promise or supply, but that is just a closure or a block of code or something like that we want to run. And we want to retry it a number of times until it throws an exception. And our retry mechanism will return a promise that will either be kept when the operation succeeds, or will be broken once all the retries are used up. So here is the solution to that. So what we do in this retry sub is we take the operation to retry, we take the intervals that we want to have as our backoff. So for example, try again after 1 second, after 2 seconds, after 4 seconds, after 8, and so on. And here I just do a for loop. I say for, and we have a bit of an interesting case. We always want to try it immediately. So we sneak a 0 in there. And the flat just means that we want to treat the 0 and the intervals in a way such that the intervals are flattened into the looping here. In Perl 6, there's a lot less sort of automatic flattening that happens. It turned out that it got very, very confusing in a lot of ways. So here we just get the backoff amount. We await that amount of time to elapse. That'll be 0 at first, so we don't really await anything at all. We try the operation, and a try block like this will, if it fails, stick an exception into $! If we are successful, we just say last. We break out of this loop. We're done. Otherwise, this last phaser here, we call it a phaser because it runs a certain phase of the program. it will run when the last iteration of the loop has been completed. And there we just take the exception that's in $! With it's like an if statement, but it's if defined, and it also sets $_ to the thing that is in the thing to the right of it there. So that just means refrow, provided we have an exception in $_. And if it's succeeded, there's nothing to refrow, so it will not do that. So this is kind of nice in that it will run the operation off on a thread. The await will just block there, and in Perl6.d, that will free up the thread to work on some other operation as well. So you won't even be blocking thread pull threads up. You'll just actually be freeing them up to do something else. So it'll scale, even better beyond the number of available threads you have then. So if we just try using it, okay, we say await, retry. This is the case where it works straight away. So there is a sequence. It's 1, 2, whatever, up to 5. And it just figures out that we must mean 1, 2, 3, 4, 5. Here is where it doesn't work out until after the third attempt. So here we just have a state variable. We increment it. We die if it's less than 3, and then eventually it works. And then we have the case where it doesn't work. It just always dies, and we retry sometimes. Attempt 1 is at 0, okay, and then we get back an exception from that retry mechanism. If the operation is asynchronous, that is, it returns a promise, so it's some kind of network operation, exactly the same code, just put an await in there. And again, it'll scale better in 6D, but already it scales across the various threads that you have. It just doesn't let you reuse the pull ones. An alternative way of writing it, I'll get to that in a second. I just wanted to mention back-off strategies. So I showed you the arithmetic progression, which is where you have 2 numbers, or you can put 3 examples, but they increase by a constant. There's also a geometric progression. So that is 2, then 4, then 8, all the way up to, say, 64. So doubling each time. Or you can do Fibonacci backoff, which can work kind of well too. Now, one problem with this is that it's not very obvious how many times it will back off. So instead, we can just say, do this up to however many elements, I don't care, it's lazy, and then just take the first 5 of them. And when you write it this way, it's very obvious not only what the sequence is, but how many things we're going to take from it, and that is how many retries we're going to do. So that's quite a nice way to write that. So another way of doing a retry is if you have a, well, actually it doesn't quite matter, and I'll explain why in a moment. But here we have a supply, and we also have a set of intervals. And I make a supply block, and I'm going to copy my set of intervals into an array remaining, and then I have a sub attempt. Okay, so we've got our own copy. We here, after tapping the supply, we emit the result if it gets it. Quit is like a catch block, except that it is for handling asynchronous exceptions. So what's the difference? Well, quit means an exception came from the thing that we tapped, okay, so from the operation that we were doing. Catch means something went wrong in the work we were doing locally. And we make a distinction from those. You often want slightly different things. Most often, you just want to let the asynchronous thing flow through you because you don't know what to do about it. So inside of there, quit works like catch. You have to smart match for it to consider the exception handled. And here we just say, well, if there's a remaining attempt, we will handle the exception by shifting off of this remaining array, and then we'll make another attempt. And that works out just fine. And one thing to notice here is that whenever actually can work on a promise, it treats it just like a single value supply. But also, this looks like it's a recursive solution because it calls attempt when we're in attempt, except it isn't, because whenever is an asynchronous loop, so its body doesn't fire until after that attempt subroutine has been left. So this isn't actually recursive at all. It's perfectly safe. Okay, so that's a supply-based retry. Now I say it's a supply-based retry, but actually whenever is quite happy to be given a promise as well, but it's also quite happy to be given any value that you like and consider it a one-value supply. In this case, you have to be a little bit careful. The quit won't quite work out there, but certainly for the case of the promise or the supply, that will work out very well. And by the way, this one does not have any problems with the await thread blocking that we discussed earlier. So you can use this one with promises today, and it'll also work out very, very well. So for the final thing I want to talk about, I've mentioned how supply blocks can be used to build up chains of operations. And you can map, you can grep, you can unique, and so on. But you can also use it to build up chains that react to incoming messages and do various interesting bits of business logic in there as well. And one of the nice things about this is that if anything crashes in the chain, it'll just tear the whole lot down, and then you can just tap it again to restart it. So you get a good way of sort of crash and restart, which again sort of borrows an idea from the actor model, I guess. So to demonstrate this, we'll look at getting some JSON messages in. We'll pass them. We'll dispatch them to a handler, and we'll have an auto restart mechanism if we crash. So passing input. Okay, well, we get an incoming supply. We just use the JSON tiny module. Use inside of a subroutine makes a lot of sense in Perl-6 because use is actually lexical. So we can just use things close to their point where we want them. And here we'll just say, whenever I get an incoming message, pass it as JSON, emit the result. Here I have an object, a make objectifier subroutine. And what this will do is it will make me something that produces a supply. And that supply will receive incoming messages in JSON form. It will look for the type field in that JSON message that has been passed, provided it was a hash that we got out of the parser. It will then check if we have anything in the class map for this type, and then it will just instantiate that class, passing the JSON in. Okay, and this is just a way that we can turn those JSON hashes into some appropriate type of class just by having a type discriminator in there. It's about the most basic JSON to object mapper we could possibly write. And there's much nicer things for doing this, like JSON class in the ecosystem as well. And then we want to process each message. So we could write this. We could write make processor. And that actually just gets a handler subroutine in, and it applies it to each of the messages. But in fact, you might just look at that and say, wait, isn't that just a long way to say map? And the answer is, yeah, it pretty much is. The only difference being that actually I didn't emit any results from this. I'm kind of assuming the message handler doesn't actually produce any results of interest. So it's not quite a map, but it's close enough. And hopefully just by looking at the supply whenever there and seeing that it's a map, it might just drive home how whenever is a lot like an asynchronous for. So finally, the automatic restart. Well, again, we'll use this quit and not recursion, but looks like it trick. So we have a run subroutine. It does whenever incoming, that just taps the supply. We don't care about any values, but if there's ever an exception, we just say whatever exception it is, note it out to the console on standard error, and then run again. That's how we can just restart our pipeline. So let's just see how this works. We have a couple of different messages here. Okay, just some simple data structures. We have a couple of multi-subroutines. Now, because our messages have been turned into types, objects, we can just use multiple dispatch to write handlers over them, and it'll just pick the correct one based on the incoming type. All we're doing there is just writing out a message. And then we need some way to plumb all of these different pieces together. And what this compose does is it takes a supply, that is the input data source, maybe coming off a message queue. It takes a bunch of stages. Each stage is something where if I call it, it will give me back a supply, and I will call it with the input supply, okay, and it will give me back a new supply. So if we just look back at what we had, okay, the first one we pass in is this pass subroutine. It gets the incoming messages, it gives back a supply of JSON. Okay, then we will give that incoming supply to this subroutine, which will give back another supply, which just does the making of objects from JSON, okay, which will pass that into this supply, which gives back the supply which handles the objects, and then we will feed that into here. And if you're fairly into functional programming, you might be looking at this and saying, wait, is that not just a really verbose way to write out a reduce? And the answer is yes, it is. Okay, but it's probably also a more understandable way. That if you're used to thinking in reduce, that is precisely what composing a supply pipeline out of different stages is. It's just reducing over them. So we make our pipeline. Okay, so I have a fake source of messages. We pass them. We turn them into objects. We process them by running the handle multi-sub of the appropriate message. And then we do an auto restart if we get an error. And then we just call pipeline.wait, which is a form of tap, which just runs the thing until it produces its final value. And because we always respawn the thing, that's just going to go on forever. So over in my virtual machine, where is my VM? There it is. Okay. So my fake data source here is every 1 second, it fakes a train code. Once in a while, it just spits out a malformed message. Most of the time, it does a delay of between 1 and 15 minutes. That QS, by the way, just mean I want to quote the string and I only want to interpolate scalars, none of the other funny things that we might interpolate. And here we just pick a cancellation reason and we send that out. So if I run this, then every second we're just going to get some kind of message. You can see we have delays, we have cancellations, and every so often there we are, we get a crash, and you can see it's respawned the pipeline, and it's keeping going there.
Interesting.
It's cool. I hate those squirrel attacks.
Yeah, damn.
It's real though.
Yeah, it really happens in some parts of the world. Okay.
Really neat.
Yep. So, do I still have 5 or 10 minutes?
Yeah. I think that'd be perfect. 5 minutes would be great.
All right. So I just want to talk just a tiny bit about concurrency and supplies. So supplies are mostly about controlling, not introducing concurrency. And what that means is that what we have assembled so far is a pipeline that will handle one message at a time. And that may be fine, but it may also be a little bit constraining, particularly if you have operations that are going to do retries and so on, or the operations themselves are asynchronous. So how might we deal with this? Well, one very easy thing we could do is just add a little bit of extra code here, say JSON parser. And whenever we get a message, a bit of JSON to pass, instead of just saying emit from JSON and pass it, we'll instead do a whenever. We'll schedule from JSON to run on the thread pool, and then whenever it gets a result, we'll get the parsed JSON there. We don't get the promise, we actually get the results from it in parsed, and we just emit that. And that gets us parallel passing of JSON of incoming messages. There's only one trade-off here, is that we have lost the order of the messages, which probably in this particular case doesn't matter, but it's something to keep in mind. Now, another thing we might wish to do is to allow our handlers to be asynchronous. And the way that we can do that is just to, instead of just calling the handler, we'll say whenever handler. And this whenever, with an empty body there, just make sure that, well, one of three things could happen. One of them is that if we get a value back, then actually nothing will happen. It will just take the value, pretend it's a one value supply, call the block, which will do nothing, and we're fine. So it works like that for just a synchronous thing. If handler returns a promise, then it means that we will wait for the promise to happen. Unfortunately, we won't actually wait because it's a whenever, okay? But what we will do is we will get any errors, and we will pass the errors on. So it's really here to make sure that if it's a promise, we don't lose the errors. It does the same if it's a supply. So we just ignore any values. And this is kind of nice because it means that it doesn't matter what sort of operation we have there, whether it's a promise, a supply, or a value, it's going to work out. So that is a way that we could run the handlers asynchronously if they already are. Okay, and I mentioned that. The other thing is that we might have handlers and we might want to just schedule them on the thread pool. So they're synchronous, but we want to run them off on threads. And all you need to do here is just stick a start statement in there, and that will just run the thing off on the thread pool. And the whenever start there is just there to make sure we don't lose any of the errors. So you might wonder why I'm not using await. Well, await actually blocks processing of further incoming messages, and that at times can be extremely useful. So one warning I should give you if you're looking at this and saying, oh great, we can go and make pipelines that spin off lots of concurrent work on lots of threads, and this will all be awesome, is that it might not be quite as awesome as you think if you have an absolute flood of messages coming in. Now I mentioned that with supplies, when you emit a value, you pay the cost of the processing downstream. And this is a very deliberate back pressure mechanism. And back pressure is something that makes sure that we don't flood our system with work to do. So if when you try to push a value through a pipeline, you have to pay the cost of that value's processing, unless something decides explicitly that that is not going to happen, it restricts the rate at which you can push values in at the top. And that is how we can get some flow control. Now, in what we have just done, unfortunately, we will have just made it so our system can be completely flooded. And depending on your use, often in production, you might have to worry about this and try to push back a little bit. And here is just a nice way of rounding off the various pieces that we've seen today to build a back pressure mechanism. So what I do here is I just keep track of in progress things that I am running, okay? And whenever I get a message into process, what I'll do is I'll take my list of in progress things and I'll just grep out those that are planned. And in progress is going to contain promises, okay? You can actually see that whenever I actually have a something in progress, I just push a promise in there, okay, that my done equals promise.new, and I keep it once the operation is done. It turns out that since I'm doing the start there, I actually could have just done a push of that as well. So there's a few ways to write this. But the important piece is here, okay?
So if there are more than 5 things in progress, we await any of them to be done. Okay, and only at the point that they are done will we then say, okay, let's go and allow more work to come in. And because await blocks further incoming messages, this means it will push backwards up the chain, and that means that you will not have that problem of messages flooding in. So there's as soon as you start to introduce more concurrency, each time we have to think, what are the consequences of that concurrency? It might be disordering. It might be that we have lost a mechanism for sort of pushing back on the incoming data to try and get some control flow. Just a quick mention, that is an interesting way to build up pipelines. You might remember much earlier on, I talked about how I could have cancellations and delays. And another way of writing these kinds of message processes is actually to have separate supplies for each event type, and then write supply blocks which are subscribing to the events they're interested in. And this can be a much more interesting setup for doing kind of complex event processing style things, which are involving lots of different event types rather than reacting to individual events on a pipeline. Okay, so just to round up with just a few quick closing thoughts from me, and then I'll turn it over for final questions. So in Perl 6, we put promise and supply right into the language. One of the reasons why is if you try and imagine writing modules in a language which didn't have a shared idea of what a string is, or what an array is, or what a hash is, it'd be really hard to write code in modules and have the modules used together. The reason that we put promise and supply into Perl 6 at the core is because we really wanted to have common interfaces to asynchronous data. And that means if you go and start looking in the module ecosystem, you will find that, for example, the module for a SSL socket is using supplies for the data arriving in over the socket or the incoming connections. And that this is actually a drop-in replacement for the built-in asynchronous socket class in Perl 6. But and if you go and take a look at the SSH module that also works asynchronously, again, that's all about supplies. So when we get that, it becomes really easy. For example, I wanted recently to build an SSH forwarding thing in Perl 6, where I just listened for local socket connections and forwarded them. And because everything was done with supplies and so forth, it was really easy to just say, well, whenever I get information on the local socket, send it to the remote one over SSH. Whenever I get data from the SSH one, send it on the local socket. And it was like 5 or 6 lines of code to ship them around. So we've got modules to be able to now do async in a really common way. Also, I say, yes, in Perl 6, you can spawn a thread manually, you can make a lock manually, you can do a condition variable. They're last resorts over using a structured style. So, always prefer to use await or supply and react blocks over doing, tapping yourself and doing callbacks, or, trying to do locking yourself and so on. There's also various modules like OO monitors, which give you structured ways of doing objects with locking too. Basically, I like to liken this to, we used to do programming with goto, and then we had the structured programming revolution. We used if statements and loops and so on. Well, supply react blocks and whenever are, the structured programming revolution for reactive programming, getting rid of all of your various callbacks, which are basically the async form of goto. It's also worth noting that Perl 6 can help. We've tried pretty hard to put a bunch of useful things in. We've tried pretty hard to think about how to try and make mechanisms where you will not shoot yourself in the foot too hard. But at the end of the day, concurrent programming is still concurrent programming. We still have to think differently. The really big thing is that time is suddenly part of the programming model. And that is where it starts getting a bit trickier to think about things because we have to start placing them on timelines. The general rule being that with synchronous programming, stuff happens in the order it's written. With asynchronous programming, nothing happens in the order it's written or in any particular order unless you do something to make that ordering happen. And last of all, just to say, the journey continues. For Perl 6 and where we are with this stuff now, to me, this is the beginning. We already know what we want to do with await in 6D. That's already prototyped. If you say use 6.d.preview, you can get this feature today. Unfortunately, you'll get a few bugs along with it, but that's coming along. One of the other things that I'm thinking quite a lot about is plans for more declarative ways to do concurrent message processing and still having the back pressure managed for you. So some of the boilerplate around that, I'm pretty optimistic we can take away in the future as well.
Just when I thought I was going to be able to ask a question you weren't going to answer in your slides, you did it again at the end there. So I was just going to ask that about if there's a more, there's going to be some tools to manage the back pressure as part of core as well, and that's good to hear.
Yeah, I mean, the basic idea, we have this idea of hyper and race in Perl 6. And the idea of hyper is that it means, normally these actually come from processing lists and doing parallel list operations, which we haven't really talked about today. But hyper means, if I do a hyper map, it's like you can run the map closure on lots of different threads, but I want the results back in order. And race means you can run them on lots of different threads, and I don't care about the ordering. But if we were to introduce, hyper whenever and race whenever, what this would mean is that we had a way to say both of you can run the whenever blocks across different threads. And I promise that it doesn't matter about the state. You'll have to, of course, know about that. You're safe to do that. But at the same time, I want to see the results of that in the same order. Or with race, I don't care about the ordering. But once we do that, we can also stick some back pressure handling there as well and sort of get some limitations into just how hyper or how racy we get. So that's the rough plan. It's easy to talk about in as a shiny idea. The semantics of it under the hood are a good bit trickier. I need some time to work through a bunch of the ways it will fall out, particularly with error handling and with tap management. It's also interesting to consider if await needs a hyper and race variant as well. So there's a lot of things that I'm thinking about in that area, and it's to try and get a more declarative way of doing this. Okay, so yeah, so I'll turn it over for any more questions, I guess. I think I've talked a bit longer than I should have done. So. Oh,
that's all right. The presentation was fantastic. I really appreciated the kind of laying out all the different problems to solve and then explaining different ways to solve them. So it covered all the topics in a really nice way. So thanks for doing that.
Yeah, you're welcome. I hope it's useful.
Yeah,
absolutely. I thought it was great.
Yeah.
Best, most Perl 6 knowledge I've had in a single. I finally feel like I'm understanding more of it for sure.
Any other questions from the group?
I don't have anything. I just want to say thank you, Jonathan, for doing this, and thank you for Nick for making it happen, scheduling it all with us. I really appreciate it.
Yeah, you're welcome.
Of course.
Very cool. All right. Well, in the interest of time, I think I'm gonna have to wrap it up here. So thanks again so much for the presentation. This will be recorded on YouTube, so those that missed it, you can send them a link later. And yeah, I think Jonathan said he'd share his slides as well, so I think that'd be great.
I will do.
Very cool. All right. Thanks so much. Really appreciate it. Worked out great.
Thanks.
All right. Yep. So have a good Friday.
You too.
Yep. Thanks.
Yeah, it's already time to go rest here in Europe. So.
Okay. Have a great night and a great
All
weekend.
right. Thanks. Yeah. See you. Take care.
Take care.
All right. Bye bye.